Okay, if you've watched the dehydration of alcohols, you should understand the mechanism. AQA don't need you to know that mechanism. But if you want to understand the chemistry, you need to know that mechanism. They just want the simplified version, which is less accurate, but will do for now. So if you can't remember how to do it with the full sulfuric acid, all you have to remember it is with a proton, an H+. Acids are just proton donors, so as long as you've got that proton at the start and you make that proton again at the end, it's still a catalyst. It doesn't matter what acid it comes from, although sulfuric acid is the one that's typically used. So this time the mechanism, pretty much the same. Lone pair on the oxygen, donate to the hydrogen, acts as, well, the H+ is acting as an acid. We've got a tertiary alcohol. You can still eliminate them. That doesn't matter. And what we're going to make this time is going to be your CH3C with a methyl group and another CH3 on it as well. And we've got our protonated alcohol. We call it protonated alcohol because it's an alcohol with an extra proton, hence protonated. That group still leaves just like it did before. Still produces our carbocation. This time it's going to be tertiary, but doesn't actually matter in this case. And we're going to have this hydrogen, the one that's going to leave, so that bond goes into the middle. And what we're going to make at the end is going to be that carbon's left with two hydrogens, double bond, CH3 up there, and a CH3 up there, so methyl propene. And the H+, which has come off there, is now left as a hydrogen plus. So that's a simplified version of the mechanism. As long as you've got the curly arrows in the right place, it doesn't matter if you don't show what's going on in the sulfuric acid. But it's important to remember that an H+ doesn't really exist on its own. It would be far too reactive to ever just be an H+. So it's better to actually remember that it is going on as a sulfuric acid molecule and then the hydrogen sulfate ion. So if we just do the same, but this time for ethanol, using the reaction mechanism where we don't have the carbocation, we're still going to have the lone pairs on the oxygen taking up that hydrogen. Probably better to put the lone pairs on just to show you actually know what's going on. And even if you don't know what's going on, try and fool the examiner that you do. Or try and fool me that you know what's going on, because that'll make me happy. Even if you're lying to me, it's nice to know that you're trying to make me believe you know what's going on. So this one, we don't create the carbocation because a primary carbocation is far too reactive, or far too unstable. So that's going to go in to form the double bond. That's the bond that breaks all at once. And you're left with a nice bit of ethene. Don't forget the water, and you've got the H+ again. I say don't forget the water. I totally forgot the water for that top reaction. Okay, so that's a simplified mechanism. If you draw that in the exam, you'll get all the marks, which would be nice. But obviously they can always make these questions slightly more complicated because that's what AQA like to do, and because simple questions are no fun for anybody. So let's have a think about butanol. Times like these, you regret drawing it displayed, although not technically displayed because I haven't drawn the bond between the oxygen and the hydrogen. Now there's two different ways this can go. If we get our H+, our acid, we're still going to go from there to there. We'll put the lone pair on there as well. And we're going to go on to this step just here. And this is where things get important. So I'm actually going to draw this one out twice. And hopefully some of you have already worked out why I'm drawing this one out twice. So I'm not going to bother drawing the carbocation stage out for this one, although it probably does exist. Or it does exist. That step there is going to happen on both of these. But the hydrogen that is lost, the hydrogen that's part of the catalyst, the one that's produced at the end again, can either be on the first carbon or it can be on the third carbon. It can come from either end. It doesn't matter. So if we break the one on the first carbon, what we're going to be left with is CH2, CH3. We're going to be left with but1e. Nice and easy. So we've got one product. Now, if we lose the hydrogen on the third carbon, this one here, we're going to have but2e. So we've got two different products, which you think, that makes sense. But you don't have two products at all. You actually have three. So we've got but1e, but2e, but what's that third product gonna be? Hopefully some of you have worked it out. The other geometric isomer of but2ene, they're on the same side. So Z but2ene, these ones are on opposite sides, so it's going to be E but2ene. So if you've got an asymmetrical, alcohol, so you've only got one carbon on this side of that carbon, two on that side, you're going to make EZ isomers and you're going to make a positional isomer as well. They love throwing those questions in because they're fun. Enjoy.